All right, so we're starting notes for 1.2, day 2. Topics today are continuity. That's the big thing today, looking at different types of continuity. And then we're also going to look at where graphs increase, decrease, and are constant. I think both of these topics you've talked a little bit about in Algebra 2, but we're going to expand on those. All right, so the most important property of functions that model real-world behavior is that they are continuous. This means that the function is continuous at a point if the graph does not come apart at that point. All right, what that means is, can you start dragging your pencil along the graph without having to pick it up at all? Okay, if you can draw it continuously, then we say it's a continuous function. All right, here's an example of one that is continuous for all x. All right, it says this graph is continuous everywhere. Notice that the graph has no breaks. This means that if we are studying the behavior of the function f for x values close to any particular real number a, we can be assured that f of x values will be close to f of a values. Now what that means is, if we define some point a, all right, and we are approaching that x value, we're approaching it along our graph. Okay, so we would be following along here. We're trying to get to that spot. We can be approaching it from either direction. But because it's continuous, as we get closer and closer and closer to that a value, our y values are matching up with the y value here when x is a. Okay, there's no break in it. We can just follow that graph along and get to that point. All right, so that one is continuous. The next few are going to be discontinuous. But there's different types of discontinuity. So our first one here and our second one look a lot alike, but there's one difference right here. We have defined f of a to be this value. All right, in other words, when x is a, we've defined this to be our y point. Okay, in this one, we haven't defined that at all. Okay, both of these are considered removable discontinuities. All right, the first one, it says this graph is continuous everywhere except for that hole at x equals a. If we are studying the behavior of this function f for x values close to a, we cannot be assured that f of x values will be close to f of a. In other words, if we start following along like we were doing on the other one, we aren't getting to f of a. F of a is way up here. Okay, so our values on this one are much lower than where f of a would be located. Okay. In this case, f of x is smaller than f of a. It's called a removable discontinuity because it can be patched by redefining f of a so as to plug the hole. All right. In other words, there is just a single point that's missing, and I can redefine this value f of a to move it down and fill that hole. Okay. So it's considered a removable discontinuity. There's something we could do to patch it up. Okay. The second one here is also a removable discontinuity. The difference here, though, is that f of a does not exist. It's not defined anywhere. We can remove the discontinuity because we can change it. We can define it to fill that hole again. Okay? So if you have a single point that's missing, either it's moved somewhere else or it's just gone completely, then it's a removable discontinuity. All right? Looking at the next two, we don't have a single point that's missing. In this one, there's a whole bunch of points that would have to be filled in to bridge that gap. All right? This is referred to as a jump discontinuity because there's more than just a hole where x equals a. There's a jump in function values that makes the gap impossible to plug with a single point. Okay? And then our last example, we call it an infinite discontinuity. Last year you referred to that as having a vertical asymptote, and we'll still use that term today. All right. but there's way more than one point that's missing, all right? And it's not just a nice little jump from one point to another. It's a whole line that's gone, okay? It's called an infinite discontinuity because you're heading towards infinity in each direction. There's no way to plug that, okay? So the first two up here would be considered removable because we can plug the hole. The second two are considered non-removable discontinuities, okay? But again, one is considered jump, one is considered a vertical asymptote or infinite discontinuity. The key concept from all of these pictures is that we want the point x f of x, or xy, to slide smoothly onto the point a f of a without missing it from either direction. Okay, so if it's continuous, you can follow that curve from each direction and you'll meet up. All right, there is no break, there's no jump, there's no vertical asymptote. It can be written with limit notation, and next year in calc you're going to do a ton of stuff with limits. All right, the notation says the limit as x approaches a of our function. In other words, as we follow that graph and get closer and closer to that x value of a, we are approaching f of a. Okay, we're meeting at that spot. All right, so a couple examples. The first ones we're going to look at involve graphs. The second set we'll look at involve just an equation. It says, judging from the graphs, which of the following figures shows functions that are discontinuous at x being 2? And then are the discontinuities removable or not? Okay, so our first one here, what do you see where x is 2? We have a vertical asymptote. All right, what did we call that? Yes, infinite discontinuity. Okay, second one, is there a discontinuity? No, this one is nice. There's no holes, there's no jumps, there's no vertical asymptotes. This would be considered continuous. How about our third picture? What? It is a removable discontinuity, yes? All right, we have a hole right there. Now, last year you probably learned about vertical asymptotes and holes in your graph, and you looked at the equations and said, why is it a hole versus a vertical asymptote? If we were to factor this, what would the top factor into? Okay. And because they share that x minus 2 factor, we could cancel it out. In other words, we can remove it. All right. So if we removed this and we looked at our this, y equals x plus 2, that's just a linear equation. And when you look at your graph, that's what you have. You have a line with a y-intercept of 2, a slope of 1, okay? And this, what I've put in the green box here, this function and the original function are identical except when x is 2. For the green function here, there would be no hole, right? It would just be a nice solid line. For my original function, there is that hole at x equals 2. If you are trying to locate where the hole should be, what you can do is eliminate the x minus 2's, just use the basic linear function here, y equals x plus 2. And when x is 2, what do we get for our y value? If we put a 2 into this function, we get a 4. Is my hole located at the point 2, 4? Okay, so when you go to graph these, that's how you can figure out where that hole should be. Okay, remove the part that's the issue, the x minus 2's here. All right, remove that and use the rest of the function to evaluate it. Okay, so that's graphically. Algebraically, it says discontinuities come from x values that result in division by 0. In other words, what makes the denominator 0. If it's removable, it's a hole in our graph. If it's not removable, it's a vertical asymptote. And how we can tell from our equation, one option is to factor it and look at what factors will drop out. The other option is to evaluate at your x value, both the numerator and the denominator. If you get 0 for a numerator and 0 for a denominator, it's a hole. If you get something other than 0 for your numerator, but you still have 0 in your denominator, it's a vertical asymptote. All right, so let's check with these. We said this one could be factored into x plus 2x minus 2. And we said we could eliminate this. Okay, so we said it was a hole. If we plug in that 2 value, h of 2, on the top, we have 2 squared minus 4, which would be 0, and we have 2 minus 2 on the bottom, which is 0. Okay, we get 0 divided by 0. That means it was a hole. If we do the same thing over here and evaluate it at 2, our denominator is 0, which is why we had the issue in the first place. But what do we get for our numerator? We get a 5. All right? So 5 divided by 0, again, we can't divide by 0, but this would indicate a vertical asymptote. Okay? All right. So the next ones we're going to analyze just based on the equation. It says find the domain of each of the following and then find the discontinuities and classify them as holes or vertical asymptotes. So the first thing we would have to do is what? Before that, factor the top. All right, we want to see if any of those factors can drop out, be removed. So take a second and just factor all 3 of them. Okay, check your factors. All right, on the first one, f of x, where is the domain issue? Where's the problem? When x is 2. Yep. So our domain here, all right, and we sometimes use subscripts to represent which function we're talking about. The domain for f would be everything except 2. So from negative infinity to 2 and then jumping over it and continuing on. Okay. Because there's an x minus 2 factor in the top and in the bottom, we could cancel these out. All right, which means it's what kind of discontinuity? Okay. So we have a removable discontinuity at x being 2. So it's what? What would show up in our graph? A hole. All right. Where is the hole located? To figure that out, we eliminate the x minus 2's and we plug a 2 in here. Yes? So we get 3. All right, let's look at the next one. G of x. Do we have any common factors that we can cancel out? All right, then it's a non-removable discontinuity, which means it's going to show up in a graph as a vertical asymptote. Yep. what would my domain be for this one? Everything but 2? Okay, so same domain as before? Negative infinity to 2, jumping it over it, and continuing on. Okay? Okay, for our third one, our t function, is it removable or not? Both answers are correct, right? There's 2 issues in this one. All right, what can my domain not be? Okay, so let's move it down here. So domain for t, we're going to start from negative infinity, go to negative 2, jump over it, go to positive 2, jump over it, and then continue on. Okay, so we do have 2 issues of discontinuity here. One at 2, one at negative 2. What type do we have at negative 2? That is removable because we can get rid of this factor. All right, so we have a removable discontinuity or a hole at x equaling negative 2. All right, if we wanted the coordinates for that, remember we put negative 2 back into our function, ignoring the 2x plus 2 factors. So if we put negative 2 in the numerator here, we get negative 8 over negative 4, which is 2. So our hole is located at negative 2, 2. All right, and then what happens at x being positive 2? Okay, so we have a vertical asymptote at x equaling a positive 2. All right, questions about that? All right, we're still looking at discontinuities, but this time you have to make the graph. I'm sure you meant to say, all right, fun stuff. And these are the great ones because these are piecewise graphs. Do you remember piecewise graphs from last year? Some of you? Okay. A piecewise graph is just 2 different, or 2 or 3, could be 4. I mean, we can have a lot of different pieces. But it's different parts of graphs kind of combined into one. All right, so when we look at this first one, we have 2 different pieces. This first one on the top here is just a linear equation. All right, so for that portion of a graph, it's going to look like a line. What is the bottom half going to look like? Okay, so we basically have a line and a parabola that we're taking chunks of each of them and merging them. Okay, this value right here describes where the change happens. So there's a change in how I've defined my function when x is 0. If it's 0 or lower, I'm going to have a line. For any x values above 0, I'm going to have a parabola. So take it in pieces. How would we graph this line? Identify your slope, your y-intercept. Slope is 1, intercept is -1. So at 0, at x being 0, our intercept here is -1. But instead of going up and to the right to draw my line, I only want this line to the left of 0. All right, so I'm going to go down and back. It still has a +1 slope. It's just that I only want that half of my line. All right, and because x can equal 0 here, we go ahead and fill it in with a solid dot. We've defined it at that point. For my parabola, what are some basic points on a parabola? Just a plain x squared parabola. 1, 1, 2, 4. All right, 1, 1, 2, 4, 3, 9, and 0, 0. Okay, now, do I include 0? No, but I have to show that I'm getting really close to that. So I use an open circle so that when I draw my parabola, it's getting really, really, really close to that open circle. It's just not at 0. Okay? So What kind of a discontinuity do we have? We have a jump discontinuity. All right, so where x is 0, there is a jump in my two pieces. There's a break there. Okay? We are going to define the domain and the range for each of these. Are there any x values that I can't use? Do I have x values over here being used? Yes, they're on the line part. Do I have x values to the right of 0? Yes, they're my parabola part. And I've defined it at 0, right? I have a solid dot there. So my domain here is everything. All right? There's no gaps in how I've defined my x's. However, there is a jump when I think of my y values. And we haven't talked a whole lot about range yet. But we're going to start always with our smallest value. So we're going to think down here at negative infinity, and we're going to just start moving up. So from negative infinity, I have y values that are included all the way up to -1. And then I jump. So I'm going to go from negative infinity to -1. Do I include the -1? Is it filled in? Okay, so then I want to do a squared bracket. But then I have a jump, and I start back again at 0 and keep going higher. Do I include 0? Okay, so rounded bracket at 0. Does that make sense? So you're just following along your y-axis from the bottom to the top and looking at what values are getting used. All right, our second one has 3 pieces to it. The first one is the same line that we had in our first example, except we haven't defined it at 0. All right, so we're going to have that same line, but we're going to have an open circle instead of a filled in one, because it can't actually hit that point. Okay. When x is 0, we have defined it to be a single dot. We just have the value of 1. So at 0, I'm up here. My y value is just a 1. Okay. All right. And then this is a parabola again. All right. So we start and have that open circle at the origin. We use the point 1, 1, 2, 4, 3, 9. Okay, so almost identical to the first one, except we have filled in the hole. Instead of having it down here at -1, we've moved it up here to +1. Okay? Is there a discontinuity? Is there a break in my y values? Yes. All right. So there is a jump, right? In other words, I can't just drag my pencil without having to move it, all right, without having to lift it. Domain. Have I used every value for x? I've defined it for less than 0, for 0, and for bigger than 0. So my domain is everything. What about my range? Start at the bottom. We start at negative infinity and we go up to -1, but this time it's not included, right? It's an open circle. Then I have a jump and I pick it up again at 0. And do I use everything above 0? Yes. So 0 to infinity is the second piece. All right, we have one more. Same line that we had before, so let's go ahead and get that graphed. This time it's filled in again on our endpoint because we've defined x to be 0 using that function. But what happened to my parabola? Yeah, it moved down one. So instead of 0, 0, I'm at 0, negative 1. And then instead of 1, 1, I'm at 1, 0. Instead of 2, 4, I'm at 2, 3. And I'm at 3, 8. So I've just moved all my parabola points down one. So by moving it down one, I've made my two pieces match up. Can I take a pencil and drag it along it without picking it up? Yeah. So this one is now continuous. Domain is everything again. And in this case, range is everything as well. All right? There's no jumps in it. All right. We are going to tackle one more topic. It's a short one. The idea of increasing and decreasing functions. I think you've talked about this last year. In this first picture, my graph is increasing. As I move from the left to the right, my y values are getting bigger. Okay. This second picture, as I move from the left to the right, my y values are going down. And in my third picture, it's considered constant since my y values aren't changing. A function is increasing for any interval if as you move left to right for your x's, your y values have a positive change, right? Think of a positive slope. It may not be linear, but it would still be going up like a positive sloping line. It is decreasing over that interval if for every positive change in x, in other words, moving left to right, my y values decrease. Okay? Slope is negative. And it's constant if my y values don't change. Slope would be 0. So our first example here, state the intervals on which the graph is increasing, decreasing, or constant. What I want you to get in the habit of doing is anytime there's a change in the direction of your graph, put a mark on your x-axis where that happens. Okay? So for this first one, there's a change at -2 and when x is +2. Because the most common mistake for students is that they get hung up on the y values because we're looking at, are my y's going up or down? And when I ask for the intervals where it's increasing or decreasing, I'm asking you to give me x values. Okay? So I want you to think of x values. All right? So starting on the left from -infinity, as we move to the right, my graph is going down until I hit this spot here. Yes? So from -infinity to -2, my graph is decreasing. What happens between -2 and +2? Okay, so from -2 to +2, in that interval, it is constant. And then at 2, it changes again. And it's the same all the way to +infinity. My graph is moving up. My y values are increasing. So from +2 to infinity, my graph is increasing. All right? So we're going to just look at 2 more pictures and identify our increasing and decreasing spots. Describe for me what this is going to look like. It is a parabola. Which way is it moved? How do we know it's a left move? How do we know it's a left move instead of an up move? Because it's in the parentheses, right? It's in the piece that's being squared. Okay, so this is a parabola that's been shifted to the left 2. All right. So at what x value is there a change in the direction of your graph? Yep, at -2. Okay, so from -infinity to -2, what is my graph doing? It is going down, right? My y values are going down. So from -infinity to -2, I am decreasing. What happens from -2 on to the right? My graph now is going up. So I'm increasing on the interval from -2 to infinity. All right, and in this picture, there was no place where I was constant. I do want to point out that when you look in your book or you're checking answers tonight, your book uses squared brackets around the endpoint numbers like this -2. You should be using rounded brackets because at a point, you aren't increasing or decreasing. It's just over an interval that you see something happening. All right, so I would not include the endpoint. All right, how about this one? If we factored the bottom, what can you tell me about that graph? Is it continuous? No. What do we have at -1 and at +1? We're going to have vertical asymptotes. Yep. All right, so here's our picture. We do have vertical asymptotes at -1 and +1. But there's also a change where else? At 0. All right, so there's a change happening here. There's something, or there's a break in my graph there. There's a break in my graph here. But there's also a change in direction at 0. All right, here my graph is going up, here my graph is going down. So any place where there's a change, indicate that on your x-axis. Okay? So taking our pieces, the leftmost piece, what is this doing? It is increasing. Yes, as you go from left to right, it's increasing. So we say increasing from -infinity to -1. And then there's a break in my graph. Okay, so now I'm going to look at my next piece. This part here is increasing between -1 and 0. And where am I decreasing? Here, from 0 to 1, and here, from 1 to infinity. Okay? All right, so topics today, the idea of continuity and increasing, decreasing. How are we feeling about those? Good? All right. Your assignment, we're going to move this 35 to 40 to tomorrow. So you're just going to do 21 to 33, and then I have a worksheet for you. Okay?